tutorial, as opposed to asking you and then waiting, I'm going to really encourage you to participate. It's very nice that people do put input into a tutorial so that it's not a lecture. We don't want to become a lecture, right? So we started with 3 particles, and they're living into the space. You think of them as 3 billiard balls or 3, billiard balls is a nice one. 3 pool balls and a pool table. Right? 1 ball, the 2 ball, and the 3 ball. So the first question I have is how many degrees of freedom does the system have? I heard someone whispering it, and it's good. If you could whisper it, you could say it out loud. How many degrees of freedom? So each ball can independently move, independently of the others, right? On the pool table. 2D table, yeah? 2D table, yeah? Very nice. So the 2D table, so you're close to this and here's the 3D. It's 6, alright? I'm getting a lot of people saying 6. Why is it 6? You want to explain? I've got a lot of people moving their hands. Okay, even though the billiard balls can rotate, I'm going to assume that I'm just worried about the way that they're moving up and down. I'm thinking of them as particles, so let's not worry about the rotation. Let's just think of each particle as being able to move up and right. So up and down, right and left. So there's 1, 2 here for this one, 1, 2 for this one, and 1, 2 for this one. 6. Each particle can move in 2 different ways. 2 for each particle, they're independent, so there's 6 degrees of freedom. Now, what are the transformation equations? What are my generalized coordinates? What should I choose for generalized coordinates? X and Y for each particle? That sounds good, I mean that's easy. So I've got x1, y1, x2, y2, x3, y3. X for the first particle, y for the first particle. X for the second particle, y for the second particle. X for the third particle, y for the third particle. They're my 6 generalized coordinates. Makes sense? Same number as there are degrees of freedom. Everything is good so far. Transformation equations between these and Cartesian coordinates for each particle, well, they're obvious. x1 is equal to x1. y1 is equal to y1. x2 is equal to x2. y2 is equal to y2. Nothing special. So let's forget this really boring situation and let's change it slightly. Now, I'm going to take a metal pole and stick 2 of the balls together with that metal pole. So let's say I stick 1 and 2 together. 1 and 2 are now connected by a metal pole. And 3 is still moving independently of them. How many degrees of freedom are there now? 5. I've got some saying 4 and some saying 5. How many of you said 4? And who's for 5? Okay, so it's kind of even split between 4 and 5. The answer is 5. And I'll tell you why. We started with 6. We added 1 constraint. 1 holonomic constraint reduced the number of degrees of freedom from 6 to 5. What was the holonomic constraint? The constraint said, let's say that this pole has a length. And let's call that length alpha. Right? So the constraint says that the distance between particle 1 and particle 2 is always going to be alpha, because there's a pole between them. So the constraint says x1 minus x2 squared plus y1 minus y2 squared is equal to L squared. Is this constraint holonomic? Yes. There's no velocities. That's holonomic. So we're happy. That means it reduces the degrees of freedom. We now know that there are therefore 5 degrees of freedom left. But we still have the problem of having to choose generalized coordinates for our system. That means we have to find 5 parameters that fully specify the system. 5 that will work directly courtesy of the implicit function theorem are x1, y1, x3, y3, and x2. And because of this constraint, I can now express y2 as a function of the others, given where the others are. So those are 5 that will work, but they're inelegant, because I have to do some square rooting, and it's just getting a little bit nasty. So in fact, there is a nicer way to parameterize the system. I can think of particle 1's position, and I know that the distance between particle 1 and particle 2 is L, and I can ask how they rotated. I mean, particle 1 and particle 2 are currently at this angle, but I mean, if I move particle 2 around, I can certainly rotate it around. I can shift particle 1 and rotate particle 2, shift particle 1 and rotate particle 2 around. So certainly another possible degree of freedom, another possible coordinate to consider is theta. Right? So, if I do that, right, I can write my generalized coordinates as x1, y1, the coordinates of particle 1. Theta, the angle from particle 1 to particle 2. x2 and x3 and y3, the coordinates of particle 3. How many are there? Number of degrees of freedom. One other thing, I need transformation equations. I need to be able to get from my generalized coordinates back to the Cartesian coordinates of every particle. This time around it's not as trivial, so it's worth writing out. Let me just take up the whole bottom half of the board here. It's not as trivial. I can write it out. x1 is equal to x1. y1 is equal to y1. Those are obvious. x2 is equal to, now there's no x2 here on this list, so I'm not allowed to use x2. What do? I started x1 and I moved theta in that direction. So I started x1. Anyone tell me what I'm going to write next? Not times, plus L times cos theta. Right, so let's check how that works. I can draw these two particles together, 1 and 2, the angle of theta from each other. The x difference here is, that's L cos theta. The y distance here is L sin theta. So from x1 to x2, I move cos theta. From y1 to y2, I move sin theta. So, what's y2 going to be? Correct. And finally, x3 and y3 are obvious. x3 is equal to x3, y3 is equal to y3. Okay, that's all very well and good. I've now added a constraint. I reduced the degrees of freedom from 6 to 5. I had a polynomial constraint, and I have generalized coordinates that neatly express the degrees of freedom of the system. Let's add another constraint. We have a metal pole shoved between particle 1 and particle 2. Now let's shove another metal pole between particle 1 and particle 3. Now there's 2 metal poles connecting these particles. The distance between 1 and 2 is fixed, and the distance between 1 and 3 is fixed. But once I fix that, I can still move them both around. Right, and let's assume that these metal poles are at slightly different axes so that I can also swap them around. And I can move the whole thing. I can shift the whole thing along, right? How many degrees of freedom do I have now? Who's saying 1, 2, 3, 4, 5. More than 5. Right. We had 6. We added a constraint, we got to 5. I added a constraint, I get to 4. Right, the majority did get that at this point. Good. So we now expect that there should be 4 generalized coordinates to express the position of the system, right? So what is the constraint? The next constraint. The next constraint was, of course, x1 minus x3 squared. This one is L, and let's call this one M. We're all alphabetical people. No, but M is mass, unfortunately. We all agree that it is holonomic. So to produce the degrees of freedom, which we claim it does, but we need 4 generalized coordinates to describe these degrees of freedom. Now we have 5 here, so we have to somehow compress things. What's the best strategy? So another angle, so the angle between the horizontal and the 3 from 1. Sure. Okay, great. So let's add. So now we have x1, y1, theta, and phi. Everybody agree with that as an idea for how we can parameterize these 4 degrees of freedom? And we can. So phi is the angle here. Theta is the angle here. Right. And so we can write our transformation equation. X1 is x1, y1 is y1, x2 is, and y2 as before, x1 plus L cos theta, y1 plus L sin theta. Finally, x3 now and y3 are given by x3 is and y3 is y1 plus d sine phi. All right. Well, we're on a roll, so let's carry on. We're getting to the climax. Once I add one more constraint, something weird is going to happen.
If this one stay.
So you're welcome to these. I mean, I'm not holding you. I know that's some of your list. Alright, so we've restricted the distance between these two and the distance between these two. Now I'm going to fix the angle with a strut between these two metal poles that fixes the angle. Right? This angle here. And I'm going to call that angle alpha. Fixed. That distance fixed. That distance B, fixed. How many degrees of freedom? 3. We went down from 4, we made 1 extra constraint, and we went to 3. Our other holonomic constraint is this case. How can we write down our constraint? Well, we can write it in terms of our theta and our phi if we want. We can write theta minus phi equals alpha, it's constant. Right? That's certainly holonomic, right? We've written it in terms of 2 of our previous coordinates. So we expect 3 degrees of freedom. The whole system now moves like a rigid thing. The whole system can translate. The whole system can rotate. What parameters can I use? X1, Y1, and phi, right? Because as soon as I know phi, I know theta. Theta from this holonomic constraint is alpha plus phi. So as soon as I know phi, I know theta. Theta is no longer a generalized coordinate. So my generalized coordinates in this case are x1, y1, and 5. Right? And then I can write my transformation equations. x1 is x1, y1 is y1, x2 and y2 were in terms of theta, so that will be x1 plus L cos of. There's no more theta, there's a 5 plus alpha. Alpha is a constant, it's not a coordinate. And x2 plus L sine 5 plus alpha. And then of course x3 and y3 is x1 plus d cos 5 and y3 is y1 plus alpha. Now the real crux comes now. At this point I add another constraint. I don't know. If something goes weird. Something strange happens. I'm going to require now, in addition to all the things that I previously required, I'm going to put a pole here. Right? So, I previously now I add that.
It's just the.
Right. So the question is, how many degrees of freedom? 2. This is what? This is 2. This is 3. I've caught lots of you in my trap. The answer is 3. It's a holonomic constraint. So you're asking, this holonomic constraint, why is it reducing the degrees of freedom? I have an answer from here.
You already have it.
Already have it. Okay, so I've got from someone already has it. So the constraint is dependent on my previous constraints. Right, and there's a way of writing that out. I want you to work out the distance between particle 3 and particle 2. This can be an exercise. I'm not going to do it now. You need to work out the distance between particle 3, distance between x2, y2, and x3, y3. Right? If you work out this distance in this picture with these coordinates, you'll realize that it is already in this picture with 3 coordinates independent of all of my coordinates. It's already fixed, it's already constant. This constraint doesn't tell me anything I didn't already know. So, the lesson there is, you've got a system, you add holonomic constraints, you have to drag them, you're reducing degrees of freedom, to come to a point at which you are at the minimum amount of constraints of the system, you add other constraints, which are not independent of the constraints, even if they're holonomic, the system does not take some back.